Okay, so a very big question here, 18 marks, predominantly related to atomic structure, but there's one or two other little bits of topics creeping in. So it goes all the way from A to H. Have a go at all of it before you go on to review your answers. So here's A, B, and C. D and D. F. G. And finally H. Okay, so let's take a look at the answers. In terms of the electron configurations, relatively straightforward, but pitfalls to avoid, mainly by reading the question carefully. What I've written out here is the electron configuration of the calcium atom, but this wants the Ca+2 ion, which means it's lost 2 electrons. So we take away the 4s2 and we're left with 1s2, 2s2, 2p6, 3s2, 3p6. On B, we're comparing the second ionisation energy of calcium to that of potassium. So I'm always going to recommend that you start this by drawing out the electron configurations or writing them out for the things that you are comparing. And I've done that here. Once I've done that, I can identify which electron is going to be lost second. In the case of potassium, it's 3p6, but in calcium, it's 4s1. So what we're seeing here is that potassium's second electron is being removed from a lower principal energy level. That means that it's closer to the nucleus, and it means that it's less shielded. So that means that potassium is going to be higher, and therefore calcium is going to be lower. In terms of identifying the S-block metal that has the highest first ionisation energy, well, we know now that it's going to be at the top of the group. That takes us down to a 50-50 answer here. It's going to be lithium or beryllium. But actually, when you compare the two, there's no difference in shielding, but beryllium has an extra proton, so you would expect beryllium to be higher. You've also done extensive work on the trend in first ionisation energy going across a period. General increase with the 2 anomalous decreases. Okay, moving on to part D, and we have got here the formula of the hydroxide of the element in group 2 from magnesium to barium that is least soluble in water. Well, this is about remembering the key facts about solubilities of hydroxides and sulfates. And the solubility of hydroxides increases as you go down the group. You simply have to remember that. That tells us that it's going to be based on magnesium. We know it's a hydroxide, and hydroxide ions are OH. To get the mark, you are then going to have to know that magnesium has a charge of +2. It's in group 2, that makes it straightforward. And hydroxide ions have a charge of -1. That means we need 2 hydroxides. Because it's a complex ion, we need the brackets. Moving on to part E, and we are dealing with a precipitation reaction, barium chloride and sodium sulfate. Now, what should immediately stand out here is that the barium and the sulfate are what will produce the precipitate. And again, that comes down to you knowing that sulfate ions, sulfates of group 2, decrease in solubility as you go down the group. And you'll be familiar with barium sulfate as part of the barium meal, part of the X-ray process. Barium ions are incredibly toxic, but because barium sulfate does not ionize or dissolve within the body, it's perfectly safe to drink. Now from there, I've got to put my barium and sulfate together. I know that barium is group 2, so it's +2. I have to know that sulfate is -2. And I'm going to make BaSO4 as a result of that. And it's really important that you include the state symbols because we have to identify that this is indeed aqueous ions making the precipitate. This is also the test for sulfate ions, you may remember. So we come across guises. Okay, now let's look at the reagent in excess. Well, I'm going to do the calculation first. I'm going to calculate my moles of BaCl2. I've colour-coded them so you can see where the numbers come from. And you'll notice I've converted my volume from cm cubed to dm cubed. That's because my concentration is in dm cubed. That gives me 1.5 by 10 to the minus 3 moles. And if I do the same for the sodium sulfate, I get 1.2 by 10 to the minus 3. So that tells me that the barium chloride is in excess. Now the next question is, what volume of the sodium sulfate would we need so that we would completely react it, so that nothing was in excess? So that tells us that we are going to need 1.5 by 10 to the minus 3 moles of BaSO4 to fully counter the 1.5 by 10 to the minus 3 BaCl2. And we also still know its concentration. It's 0.15 mole dm to the minus 3, which gives us a volume of 0.01 decimeter cubed. Alternatively, you may have written that down as 10 centimeters cubed. Part F. And this is one of the more complicated varieties of mass spec calculations, but actually there is a fairly set route that you can take through something like this. So we've got three isotopes, 86, 87, 88. We know nothing about 88, but we do know that 86 and 87 have an equal abundance. Now that helps us as we go through the calculation. I'm going to start first of all with why the isotopes have identical chemical properties. It's because they have the same electronic structure. So they each need to lose 2 electrons to react. Therefore, no difference. The calculation itself, well, I don't know what the percentage of 86 and 87 are, but I know they're equal. So I'm going to say that they are X. And if they're both X, I know that 88, based on percentages, is going to be 100 take away 2X. So I've set up my mass spec calculation in the normal way, but I've added some algebraic functions. Once I've done that, I need to start to rearrange to make X the subject. So I multiply both sides by 100. I then get all of the X's on one side, and then I've got the numbers on the other. I then simplify. I've got negative 30 is negative 3x, and therefore x equals 10. Now, if that tells me the percentage abundance of 86 is 10 and 87 is 10, then 100 take away that 10 plus 10 gives me 80. So it's 80% strontium 88. If you take a look at the number 87.7, very, very close to the 88, looking at the bigger picture here, I would expect it to be quite a high percentage of 88 to get to that value. Okay, moving on to part G, we have got here time of flight mass spectrum, and we've got ions of barium 136, 137 and 138. Which of these has the longest time of flight? Which is slowest? Well, remember, in the acceleration phase, they are all accelerated to an equal kinetic energy. Now, larger particles with the same kinetic energy will move more slowly and therefore take longer. For that reason, we're going for the biggest isotope, barium 138. But I've not got the mark because the question asks for us to identify the ion. And in the mass spectra, or the mass spectrum, it's going to be a plus charge. So that absolutely has to be included. Moving on to part H, and again, quite a familiar question here. As the bank of these questions builds, you will see far more of them, and they all follow a fairly similar route through. So I'm going to colour code it so you can see where the numbers are coming from. Hopefully it will all make sense. First of all, I need to know the mass of a 137 Ba plus ion, because we've got lots of information about it, but we don't have its mass. We have its relative atomic mass, and we know how many atoms or ions are in a mole. So that takes me to my answer. However, that would give it me in grams. I need it to be in kilograms. So I'm actually going to divide the whole thing by 1,000 as well. And that gives me 2.275 by 10 to the minus 22 kilograms. Now from there, I can take my KE is half mv squared and I can start to rearrange it. I want V, so I get to V is root 2KE over M. And again, I can start to put those figures in. 2 times kinetic energy. Well, kinetic energy was provided. I've highlighted that in pink. And we are dividing by the mass that we've just calculated that I've highlighted in orange. And that gives me a velocity, 5.6646 by 10 to the 4 meters per second. Now from there, bearing in mind I need to know distance, I need to know the length of the tube, I'm going to take my d and calculate velocity times time. Again, I'm colour coding to see where those numbers are coming from, and once I put all of those together, I will get to a value of 1.53 meters. And I've highlighted there the appropriate number of significant figures. We can't go higher than 3 significant figures because that's what we have been given through the course of the question.